Hello and welcome to this course by Compylo designed to help you with the common questions being asked in most of the interviews based on PySpark and SparkSQL. In this series, we will explore PySpark, which is playing a crucial role in modern data processing and analytics. But before that, let me discuss Python and Spark. So, Python is a versatile programming language that has become the go-to choice for data scientists and engineers. Its simplicity and readability makes it an excellent tool for data manipulation, analysis, and visualization. With a rich ecosystem of libraries, Python sets the foundation for data exploration. Whereas Apache Spark is an open source distributed computing system that has revolutionized how we handle large datasets. Known for its speed and efficiency, Spark allows for in-memory data processing, significantly reducing the time required for data analysis. It supports various programming languages, but today we will focus on how it seamlessly integrates with Python. Now, let's discuss PySpark. See, PySpark is the Python API for Apache Spark, enabling you to write Spark applications using Python. With PySpark, you can take advantage of Spark's powerful distributed computing capabilities while leveraging the simplicity of Python. We can use assorted IDEs like Jupyter Notebook, PyCharm, Visual Studio Code, Apache Zeppelin, Eclipse with PyDev, and Google Colab to write code in PySpark. Additionally, we have SparkSQL, which brings SQL-like capabilities to Spark, allowing you to run SQL queries on large datasets. It enables users to query structured data efficiently and is particularly useful for those familiar with traditional SQL. One more thing, many of us get confused about the differences between PySpark and SparkSQL. So, to clear the air, let me read the sentence from official documentation. And let's see what is written in the box highlighted. It says PySpark supports all the Spark's features such as SparkSQL, DataFrames, structured streaming, machine learning, and Spark Core. What does this mean? This means we can safely say that SparkSQL is a subset of PySpark. What are the different ways to deploy and manage PySpark applications? Deploying and managing PySpark applications can be achieved through various methods, depending on specific requirements of our environment and the complexity of our application. We can use tools like Databricks, AWS EMR, Azure HD Insight, Jupyter Notebook, Apache Airflow, Kubernetes, and Apache Mesos. Let's discuss them one by one. Databricks is a cloud-based platform that provides a collaborative environment for big data and machine learning with Spark. It offers built-in job scheduling, dashboards, and monitoring features, making it easier to develop and manage Spark applications. AWS EMR, that is Elastic MapReduce, is a managed service that simplifies running big data framework like Spark on AWS. We can launch Spark clusters, manage scaling, and monitor job execution using the AWS Management Console or CLI. EMR also integrates with other AWS services. Azure HD Insight is a fully managed cloud service that makes it easy to process big data using Spark. We can create Spark clusters, submit jobs, and monitor performance through the Azure portal. Jupyter Notebooks can run PySpark within Jupyter Notebooks for interactive data analysis and exploration. While not suitable for production, it is great for prototyping and testing. We can use PySpark in Jupyter to run commands interactively. Apache Airflow is used for orchestrating Spark jobs as part of a data pipeline. We can define our workflows as DAGs in Airflow and schedule Spark jobs accordingly. Kubernetes is a popular container orchestration platform that can manage Spark applications in containers. We can deploy Spark applications as pods, enabling scaling, monitoring, and management using Kubernetes tools. We can use the Spark operator for Kubernetes to simplify deployment and management. And finally, Apache Mesos is a cluster manager that can manage resources across different frameworks, including Spark. We can deploy Spark on top of Mesos and benefit from its resource scheduling capabilities. This is useful for multi-tenant environments. Next question is, how would you monitor and troubleshoot PySpark jobs running in a production environment? Monitoring and troubleshooting PySpark jobs in a production environment is essential for maintaining performance, reliability, and efficient resource usage. There are a couple of approaches that can be used for this. And approaches are Spark Web UI, log level, and external monitoring solutions. Let's discuss them one by one. Spark Web UI provides detailed insight of job execution, including stages, tasks, and executors, along with a check for failed stages and the reasons behind them. We can set appropriate logging levels like info, warning, and error in our Spark configuration to capture relevant information without overwhelming log files. We can also integrate with monitoring tools like Grafana, Prometheus, Datadog, or New Relic to visualize metrics over time and set up alert for anomalies. Next question is, what is PySpark? See, we have been discussing PySpark interview questions from long time, but generally this question can come as a first question in any interview with an intent to check your basics. So, PySpark is the Python API for Apache Spark and open source distributed computing system designed for big data processing. It allows users to leverage the power of Spark through Python, making it easier to perform data analysis and build machine learning models on large datasets. It supports Spark's features like Spark Dataframe, SparkSQL, Spark Streaming, Spark ML Lib, and Spark Core. It also provides an interactive PySpark shell to analyze structured and semi-structured data in a distributed environment. PySpark basically supports reading data from multiple sources and different formats. And we can use following command to install PySpark, which is pip install PySpark. Next question is, what is a user-defined function in PySpark? A user-defined function, that is UDF, in PySpark is a way to define custom functions that can be applied to data frames. UDFs allow you to extend the built-in functionality of Spark by writing our own transformations and operations on data. In PySpark, UDFs can be created by creating a Python function and wrapping it with PySpark's SQL UDF method to use it on DataFrames or SQL. These are generally created when we do not have the functionalities supported in PySpark library and we must use our own logic in the data. UDFs can be reused for any number of SQL expressions or data frames. Next question is, what are the types of PySpark's shared variable and why they are useful? In PySpark, shared variables are variables that can be used across multiple tasks in a distributed manner. They are essential for managing state and sharing data efficiently among the nodes in a Spark cluster. The two main types of shared variable in PySpark are broadcast variable and accumulator variable. Let's first discuss about broadcast variable. Broadcast variables allow us to efficiently share large read-only data across all worker nodes. Instead of sending the data with every task, Spark sends the broadcast variable to each node once, and each task can access it from local memory. When it comes to benefits, broadcast variables reduce the amount of data that needs to be sent over the network and hence improves the performance. Also, they make it easier to use large datasets that need to be referenced by multiple tasks. Now, accumulator variables are used to aggregate values across the nodes. They can be incremented by tasks running on the cluster, and the updated value can be retrieved by the driver program. Accumulators are primarily used for counter and sums. When it comes to benefit, accumulator variables are useful for tracking metrics during the execution of jobs. Also, they are thread safe and can be safely used in parallel processing environment. Next question is, what is SparkSession in PySpark and why is it important? SparkSession serves as the entry point to PySpark and replaces SparkContext starting from version 2.0. It acts as a gateway to all PySpark functionalities related to RDDs, DataFrames, datasets, and more. Additionally, it provides a unified API that consolidates the role of SQL context, streaming context, Hive context, and other contexts. Internally, SparkSession creates SparkContext and SparkConfig based on the configurations specified. We can create a SparkSession using the builder pattern. A SparkSession is essential for creating a data frame or dataset in PySpark. Next question is a mix of 3 questions. What do you know about PySpark data frames? What are their advantages? And do we have any alternative for them? A PySpark data frame is a distributed collection of structured data akin to tables in relational databases, organized into named columns. Compared to R or Python, PySpark data frames offer improved optimization. They can be created from various sources, including Hive tables, structured data files, existing RDDs, and external databases. The data in a PySpark data frame is distributed across multiple machines in the cluster, enabling operations to be executed in parallel on all nodes. This structure allows them to manage large volume of structured or semi-structured data, scaling up to petabytes. When it comes to advantages, data frames are optimized for performance, allowing Spark to execute operations more quickly than using traditional RDDs. Data frames are designed to handle large datasets, taking advantage of Spark's distributed computing capabilities. Also, they support a variety of data formats and sources, making it easier to work with diverse datasets. When we talk about the alternatives of PySpark data frames, first thing that comes in our mind is RDDs, that is resilient distributed datasets, which are the core abstraction in Spark and allow for distributed data processing. However, they are lower level compared to data frames and lack built-in optimization features, making data frames a more efficient choice for structured data. Next alternative is Pandas data frame. For smaller datasets that fit in memory, we might use Pandas data frame in Python. However, Pandas does not support distributed computing, making it unsuitable for large-scale processing. We can also talk about Dask data frames. Basically, Dask is a parallel computing library that provides a similar data frame interface as Pandas, enabling larger than memory computations across a cluster. While not a direct alternative, it can be used for similar use cases in a distributed manner. And finally, Koalas. Koalas is a library that provides a Pandas-like API on top of Apache Spark. It aims to simplify transition between Pandas and PySpark DataFrames, making it easier for Pandas users to leverage Spark distributed capabilities. PySpark DataFrames are a powerful tool for handling large datasets efficiently in a distributed environment. Their ease of use, performance optimization, and integration with Spark's SQL capabilities make them essential for data processing and analysis in big data applications. While there are alternatives like RDDs and Pandas data frames provide a more efficient and user-friendly approach for structured data tasks in PySpark. Next question is PySpark faster than Pandas? Although timing of this question might not look correct, as we have already discussed little bit about this, but the speed comparison between PySpark and Pandas largely depends on the context in which each library is used, including the size of data, the type of operations being performed, and computing environment. PySpark is faster for large datasets that exceed the memory limits of a single machine, as it is designed for distributed computing. It can handle the data in the range of terabytes to petabytes across multiple nodes in a cluster. Pandas is faster for small to medium datasets that fit into memory due to lower overhead from not needing to distribute data across a cluster. So, directly saying yes, PySpark is faster than Pandas may not be a suitable answer. Next question is, what are the advantages of PySpark RDD? See, while RDDs provide powerful capabilities for distributed data processing, it is worth noting that PySpark's DataFrame and Datasets offer higher level abstraction with optimizations and easier APIs for handling structured data. In many cases, DataFrames may be preferred for performance and ease of use, but RDDs remain a valuable tool, especially for low-level operations and unstructured data. Since question asks about RDD, let's discuss about the advantages. The first advantage is fault tolerance. RDDs are designed to be resilient, meaning they can recover from failures. If a partition of an RDD is lost, Spark can recompute it using the lineage information of the transformations applied to create that RDD. RDDs are immutable, meaning once created, they cannot be changed. This property helps preventing issues related to shared state and ensures consistent data processing across distributed systems. Operations on RDDs are evaluated lazily. This means transformations are not executed until an action like collect or count is called. This allows Spark to optimize the execution plan and reduce the amount of data shuffled across the network. RDDs allow data to be distributed across multiple nodes in a cluster, enabling parallel processing. This significantly speeds up the execution of large-scale data processing tasks. RDDs support various operations including transformations like map, filter, flat map, and actions like collect, reduce, count, making them versatile for a wide range of data processing tasks. RDDs can be created from various data sources, including local files, HDFS, and other distributed storage systems. This flexibility makes them suitable for diverse data ingestion scenarios. Also, RDDs allow users to control the partitioning of data, enabling optimized performance for certain operations and better resource utilization across the cluster. RDDs can be easily converted to and from data frames and datasets, allowing users to leverage the benefits of both RDDs and Spark's higher level APIs. And finally, RDDs can handle complex data manipulations and transformations, which can be useful for advanced analytics and custom algorithms. Next question is, what are the different cluster manager types supported by PySpark. PySpark supports several cluster managers that help in managing resources and scheduling tasks across a distributed computing environment. A few main cluster managers supported by PySpark are shown on the screen. Standalone cluster manager is the simplest cluster manager provided by Spark. It is easy to set up and configure, which makes it suitable for small to medium-sized applications. For this, no external dependencies are required and it supports both local and cluster mode. Also, it can manage Spark's resource allocation and scheduling. Apache Mesos is a general purpose cluster manager that can run different types of workloads, not just Spark jobs. In this, dynamic resource allocation allows for sharing resources between different applications. It has fault tolerance capabilities and can manage both long-running services and batch jobs. Hadoop Yarn means yet another resource negotiator is the resource management layer of the Hadoop ecosystem. It allows multiple data processing engines, including Spark, to run and share resources on a Hadoop cluster. It supports dynamic allocation of resources based on demand and provides fine-grained scheduling and resource management. It also integrates well with other Hadoop components such as HDFS. And finally, Kubernetes is an open source platform for automating the deployment, scaling, and management of containerized applications. PySpark can run on Kubernetes as a cluster manager. It supports containerization, making it easy to deploy and manage Spark application in a cloud-native environment, and offers scalability and fault tolerance. It utilizes Kubernetes built-in features for resource management and scheduling. Each cluster manager has its strengths and suitable for different use cases. The choice of cluster manager depends on factors like existing infrastructure, the scaling of application, resource management needs, and the complexity of the deployment. PySpark's flexibility allows users to leverage any of these cluster managers to effectively run distributed data processing jobs. Next question is, what are the common algorithms supported by PySpark's machine learning API? PySpark's machine learning API, known as MLlib, provides a wide range of algorithms for various machine learning tasks. Widely, we can divide them into classification algorithm, regression algorithm, clustering algorithm, and dimensionality reduction. Under classification algorithm, we have logistic regression, decision trees, random forest, gradient boost trees, and naive Bayes. Under regression algorithms, we have linear regression. Under clustering algorithm, we have k-means clustering, then Gaussian mixed model, then bisecting k-means. Then we have collaborative filtering. And after that, we have dimensionality reduction, under which we have PCA, which is principal component analysis, and SVD, which is singular value decomposition. After that, we have feature extraction and transformation, where we use term frequency inverse document frequency, which is TF-IDF, and then count vectorizer. And finally, we have pipeline APIs. To conclude, PySpark's MLlib offers a comprehensive suite of machine learning algorithms suitable for various tasks, including classification, regression, clustering, and recommendation. Its ability to handle large datasets in a distributed manner makes it a powerful tool for data scientists and engineers working on big data projects. Next question is, what are RDDs in PySpark? RDDs, or resilient distributed datasets, are a fundamental data structures in PySpark. RDDs are designed to handle large-scale data processing in a distributed environment. RDDs automatically recover lost data due to node failures through lineage information, which tracks the sequence of operations that created the dataset. RDDs are distributed across multiple nodes in a cluster, which allows for parallel processing of data, which significantly speeds up the data operations. And once RDD is created, it cannot be modified. Any transformation applied to an RDD results in a new RDD. This immutability helps maintaining data consistency and simplifies fault tolerance. We can perform multiple operations on RDD for certain tasks. These operations can be of two types: transformation and action. The transformations, when applied on RDDs, result in the creation of a new RDD. Some of the examples of transformation operators are filter, group by, map. Actions: these operations instruct Spark to perform some computation on the RDD and return the result to the driver. It sends the data from executor to the driver. Some examples are count, collect, and take. Finally, RDDs are a powerful abstraction of distributed data processing in PySpark, allowing for efficient handling of large datasets with resilience and flexibility. While newer APIs like DataFrames and Datasets are often preferred for complex data manipulation due to their optimizations, RDDs remain crucial for understanding the underlying mechanism of Spark. Next question is, what are PySpark serializers? When we perform operations in PySpark, such as creating RDDs or broadcasting variables, Spark serializes the objects involved to send them to worker nodes. This serialization and deserialization process happens automatically, and choosing the right serializer can significantly impact the performance of our Spark applications. The serialization process plays a crucial role in optimizing performance in Spark. Data transferred over the network to disk or memory needs to be preserved, and PySpark provides serializers for this task. Let's discuss about two main types of serializers. First is pickle serializer and second is Marshall serializer. Pickle serializer utilizes Python's pickle module and can handle nearly all Python objects. Marshall serializer offers faster performance than pickle serializer but supports a more limited range of object types. Basically, serializers in PySpark are vital for efficient data handling in a distributed environment. Our choice affects the speed and efficiency of data transfer, so it is important to select the appropriate serializer based on your specific use case. Next question is, why do we use PySpark SparkFiles? SparkFiles in PySpark are used to manage and distribute files across the nodes of a Spark cluster. When we need to use external files such as configuration files, scripts, or other data files in our Spark application, SparkFiles helps in efficiently making these files accessible to all worker nodes. This functionality is available through SparkContext and can be accessed using sc.addFile method, which is used to load file into Spark. You can retrieve the file path with the SparkFiles.get method, and additionally, SparkFiles help to resolve paths for files added via sc.addFile, where sc represents SparkContext. Using SparkFiles in PySpark is essential for efficiently managing external files and dependencies across a distributed cluster. It simplifies file distribution, ensures consistency, and improves performance, making it a valuable feature for building robust Spark applications. Next question is, what is SparkContext in PySpark? You must have heard me saying a term called SparkContext in previous question. So let's elaborate it here. SparkContext was a fundamental entry point for any Spark application in PySpark. It served as the main connection to a Spark cluster and provided various functionalities necessary for building and managing Spark applications. Now we use SparkSession from Spark 2.0 onwards, which includes SparkContext for real computation. Let's discuss about a couple of key features of SparkContext. SparkContext establishes a connection to the Spark cluster, allowing your application to access the resources of the cluster. And when I say resources, I mean computing power and memory. SparkContext provides methods to create RDDs, which are the primary data structure in Spark for distributed data processing. For example, we can create RDDs from existing data in memory or from external data sources like files. SparkContext manages the allocation of resources across the cluster, distributing tasks and monitoring their execution. We can configure various settings for our Spark application using SparkConf, which can be passed when creating a SparkContext. It includes setting of memory allocation, execution mode, and more. Also, SparkContext handles the scheduling of jobs and tasks across the nodes in the cluster, ensuring efficient execution of our data processing tasks. And finally, through SparkContext, we can access other components of the Spark ecosystem, such as SQL context for working with structured data, streaming context for streaming processing, and Hive context for interacting with Hive. SparkContext has been crucial for developing Spark applications in PySpark, as it facilitated the creation of RDDs, managed resources, and enabled access to the Spark ecosystem. Understanding how to use SparkContext effectively can be essential for optimizing performance and efficiently processing large datasets in a distributed environment. Next question is, what would happen if we lose RDD partitions due to the failure of the worker node? If an RDD partition is lost due to the failure of a worker node, Spark's resilience feature comes into play to handle the situation. Here is what happens. RDDs are built using transformations, and Spark maintains a lineage graph that records the sequence of operations that created the RDD. This lineage information is used to recompute lost partitions. When a worker node fails and an RDD partition is lost, Spark can re-execute the necessary transformations from the original data to regenerate that partition. This process is called recomputation. The recomputation is handled automatically by Spark. As a user, we don't need to manually intervene. Spark takes care of recovering the lost data. Although recomputing lost partition may introduce some overhead, the process ensures that your application continues running without significant disruption. If we are using a data source that supports replication, like HDFS, the original data might be available on another node. In such cases, Spark can read from the replicated data, avoiding the need of recomputation. While the system can recover from the loss of partitions, this may increase the overall job completion time, especially if many partitions need to be recomputed. Spark automatically retries tasks that failed due to worker node issues. If a node fails, the tasks associated with that node are scheduled to run on available nodes. And finally, Spark provides monitoring tools to help us in understanding task failures, which includes which partitions were lost and how they were recovered. This information can be valuable for debugging and optimizing our applications. So in summary, if an RDD partition is lost due to a worker node failure, Spark utilizes its lineage information to automatically recompute the lost partition. ensuring fault tolerance. While this may introduce some performance overhead, the system's ability to recover transparently allows our application to continue running effectively. Next question is, what do you understand by PySpark streaming and how do you stream data using TCP/IP protocol? PySpark streaming is an extension of the core Apache Spark API that enables processing of real-time data streams from data sources like TCP socket, S3, Kafka, Twitter, file system folders, etc. The processed data can be sent to databases, live dashboards, HDFS, Kafka, etc. It allows us to build applications that can process live data streams, which is essential for use cases like real-time analytics, monitoring, and event detection. PySpark's streaming is designed to handle continuous data streams and perform computations on them in micro batches. To stream data from a TCP socket, we can utilize readStream.format method of the SparkSession object. This method allows us to specify the streaming source by providing the host and port as options. Similarly, we can use writeStream to write streaming data frame or dataset. So to conclude, PySpark streaming is a powerful tool for processing real-time data streams. By leveraging TCP/IP protocols, we can easily create applications that react to live data, enabling a variety of use cases in analytics, monitoring, and event-driven architecture. Next question is, what is PySpark SQL? PySpark SQL or SparkSQL is the most widely used module in PySpark for processing structured columnar data. Once a data frame is created, we can interact with the data using SQL syntax. SparkSQL enables the execution of native SQL queries in Spark, allowing operations like select, where, group by, join, and union. To use SparkSQL, the initial step is to create a temporary table from the data frame using the create or replace temp view function. After its creation, the table can be accessed throughout the SparkSession using the SQL method. The temporary table will be dropped when the SparkSession is terminated. Let us see this example where what we are doing is from line number 6 to 9, we have prepared a data with name, age, gender, and marks in science. And after that, at line number 12, we have created the data frame using this data. So if you see the data that we are showing using .show function, so we have the name, age, gender, and marks in science. After that, what we are doing here is we are using create or replace temp view to create a temporary table. And finally, we are using a select asterisk from science students, which is a temporary table that we have created. And if you see, it is showing me all the data. In this section, what we are doing is we are selecting the gender and the gender count. And you can clearly see that we have one female and two males here. So by this way, we can use SparkSQL for our analysis. Next question is, what do you understand by PySpark's StartsWith and EndsWith methods? In PySpark, StartsWith and EndsWith methods are used to filter data frame columns based on string patterns. These methods are particularly useful for string operations when we want to check whether the values in a specific column start or end with a given substring. Both these methods are case sensitive by default. For instance, a string written in caps or in small will not match. Also, these methods return a Boolean result, which can be used for filtering the data frames. So as you can see on the screen, what we have done is we have created the data frame in line number 7 using the data available at line number 6. It's a single column data frame. And now what we are doing is we have used the filter function along with StartsWith to filter the row which starts with C. And finally in the last snip we can see that we are using EndsWith O, so we are getting 2 rows as an output. Next question is it possible to create PySpark data frame from external data sources? And the answer would be yes. It is entirely possible to create a PySpark data frame from various external data sources. PySpark provides built-in support for reading data from multiple formats and sources, enabling users to easily load and process data from different locations. Some common external data sources from which we can create a PySpark data frame are CSV, JSON, and Parquet. PySpark also supports text, Avro, TSV, and many other file extensions. This capability allows for efficient data processing and analysis, leveraging the power of Spark's distributed computing framework. How can we create data frames in PySpark? Although you must have seen many code examples in previous questions, but considering it as a new question, let us discuss this. We can do it by making use of create data frame method of the SparkSession as shown below. So here you can see at line number 6 we have the data, and at line number 7 we are using create data frame to create the data frame in PySpark. Next question is, what are the different approaches for creating RDD in PySpark? In PySpark, we can create RDDs using several approaches, like the first one is from existing data frames. So as you can see, we have specified data at line number 5 and we have created the data frame at line number 7. And after that at line number 9, we are converting that data frame to RDD. We can also use collection, which is list or tuple. So we can create an RDD directly from a Python collection such as list or tuple using the parallelize method. So as you can see here, we have the data at line number 4 and we are using SparkContext.parallelize method to convert it into RDD. There is another way, which is from external data sources. We can create RDDs from external data sources such as text files, CSV files, or JSON files using the text file method or other file reading methods. So as you can see here, we are using text file in the second screenshot. One more approach is from existing RDDs. We can transform an existing RDD to create a new RDD using transformations like map. So here what you can see at line number 4, we are using map function to convert it into a new RDD. There is another way, using the whole text files method. We can create RDDs from a directory of text files where each file is treated as a single record. So here we are using whole text file method to refer to a directory. See, creating RDDs in PySpark can be accomplished through various methods, and this flexibility allows for efficient data processing in distributed environments. Next question is, how do we create SparkSession? To create a SparkSession, we use the builder pattern. The SparkSession class from the PySpark.sql library includes the get or create function, which creates a new SparkSession if one doesn't already exist. Otherwise, it returns the existing SparkSession object. You can see on the screen, the first screenshot shows how to create a SparkSession, which has a builder pattern from line number 3 onwards. So at first we are importing SparkSession, and then we are specifying the app name, then we are setting the config, and then we are using get or create method. Here, builder is the method that helps in constructing a new SparkSession. The app name sets the name of our application, which can be useful for tracking purposes. The config is used for setting various Spark configuration, but it is optional. And get or create, this method will either create a new Spark session if one doesn't exist or return the existing one. However, if we want to create a new Spark session object every time, we can use the new session method as shown in the second screenshot. Next question is how to profile in PySpark. And to answer this, let us refer the official documentation. So this documentation is from Databricks, and you can read the highlighted section which says PySpark profilers provide information such as the number of function calls, total time spent in the given function, file name, as well as line number to help navigation. That information is essential for exposing tight loops in your PySpark programs and allowing you to make performance improvement decisions. Next question is, how do you create PySpark UDF? See, we have already discussed a little bit about UDFs earlier, but here creating a user-defined function in PySpark allows us to extend the functionality of SparkSQL by writing our own function in Python. We can use following steps for a UDF in PySpark. First one is we need to import the necessary PySpark modules including SparkSession and UDF. After that, we can create a SparkSession, which is the entry point for using PySpark. Next step is writing a Python function that we want to use as a UDF. Then we can use UDF decorator to register it as a UDF, specifying the return type. And finally, we can apply the UDF to DataFrame columns using the with column, select or filter methods. Let us discuss an example of how to create a simple UDF that converts string to uppercase. So here, what we are doing is we have used builder function with app name and get or create. And after that, we have defined two uppercase user-defined function where it is using s.upper function to convert the lowercase to uppercase. And at line number 12, what we are doing is we are using the UDF decorator. Now, let us see that what data we have. At line number 2, we can see we have this data which we have converted into data frame at line number 3. And finally, we are using with column activity to convert the lowercase to uppercase. And finally, when we see the data using the show function, so we can see the names have been converted to uppercase. And if you notice, it has not converted null to uppercase. Now, let's discuss a couple of points to remember. UDFs can be less efficient than built-in functions because they require serialization and deserialization of data. We should make sure to specify the correct return type when defining a UDF. And it is a good practice to handle potential none values within the UDF to avoid runtime errors. What are the main advantages of using PySpark over traditional Python for big data processing? See, using PySpark for big data processing offers several key advantages over traditional Python. The first one is scalability. See, PySpark can handle large data sets across a distributed computing environment. It can scale from a single machine to thousands of nodes, making it suitable for big data applications. Next is speed. PySpark leverages in-memory processing and optimized execution plans to improve performance. This is especially beneficial for iterative algorithms and operations on large datasets. Third is fault tolerance. PySpark automatically handles node failures through its resilient distributed datasets, that is RDD abstraction, ensuring that your data processing continues seamlessly. Fourth is data parallelism. PySpark distributes data and computation across multiple nodes, allowing for parallel processing, which significantly reduces processing time compared to single-threaded Python. Fifth point is integration with big data ecosystem. PySpark integrates well with other big data tools like Hadoop, Hive, and Kafka, allowing for a seamless data pipeline and processing workflow. Next point is support for complex data types. PySpark natively supports various data formats, including structured and semi-structured data like JSON, making it easier to work with diverse data sources. Next point is rich API. PySpark offers a rich set of APIs for data manipulation and machine learning, enabling users to perform complex data transformations. Eighth point is machine learning capabilities. PySpark's ML provide scalable machine learning algorithms that can operate on large datasets, making it easier to implement machine learning workflows in big data scenarios. Next point is community and ecosystem. As part of Apache Spark ecosystem, PySpark benefits from a large community, extensive documentation, and ongoing contributions, ensuring access to a wealth of resources and support. And last point is SQL support. PySpark includes SparkSQL, which allows users to run SQL queries on large datasets, making it easier for those familiar with SQL to engage in data analysis. So in summary, PySpark is optimized for big data processing, offering speed, scalability, and comprehensive set of tools that surpass what traditional Python can provide in a big data context. Next question is, what are the different ways to read data into PySpark? So, PySpark supports reading data from various sources such as CSV, Parquet, and JSON. For this, it provides different methods as you can see on the screen. So when we need to read data from CSV files, we can specify options like header, delimiter, and schema with spark.read.csv function. Similarly, we have spark.read.json function for JSON files, which supports nested structure and various options for parsing. When it comes to Parquet files, Parquet is a columnar storage format which is optimized for performance, and we can use spark.read.parquet. We can also read text files using spark.read.text, which returns an RDD of strings where each line in the file is an element in the RDD. We can also read data from databases, and spark.read.jdbc supports various databases like MySQL, Postgres, and Oracle. Along with this, we can read data from Hive tables, ORC files, Avro files, external sources like Kafka, and data sources using APIs. Next question is, how do you handle missing data in PySpark? So we have various options as you can see on the screen. So let's discuss them one by one. First is filtering rows with missing values. We can filter out rows that contain null values using the filter or drop NA method. So in the first screenshot, you can see we have used filter method as well as drop NA method to do so. Next approach is filling missing values. You can fill missing values with specific values or using method like forward filling or backward filling. So as you can see on the second screenshot, we are using mean of the values for filling them. Additionally, if you notice the first screenshot on this screen, we can aggregate data while ignoring nulls using functions like count, average, etc., which automatically skip null values. Next option could be replacing missing values. And in this code, if you want to replace missing values based on some logic, you can use the when and otherwise functions from PySpark.sql.functions module. Additionally, we can use replace function, as you can see on the third screenshot of this screen. And next option is imputing missing values. See, for more advanced techniques, you can use machine learning models to impute missing values. This typically involves training a model on the complete cases and predicting values for the missing entries. One more option that we can discuss is using SQL expressions. If you are working with Spark SQL, you can handle missing values using SQL syntax. So to summarize, we have many options to handle missing values. Okay, we can start with filtering rows, then we can fill missing values, then we can replace missing values, then we can impute missing values, or we can use the SQL for this. Next question is, how can you cache data in PySpark to improve performance? And what are the benefits of caching? See, caching data in PySpark can significantly improve performance by avoiding repeated computations and reducing the need for data serialization and deserialization, especially when dealing with large datasets that are accessed multiple times. Now, how to cache data in PySpark? So first could be using cache method, as you can see on the screen. So you can cache a data frame or RDD using cache method. This stores the data in memory for quicker access on subsequent operations. Next option is using persist method. The persist method allows you to specify different storage levels, such as storing data in memory, on disk, or a combination of both. This is useful for tuning performance based on available resources. And common storage levels are like memory only, memory and disk only, memory only, SER. And here we have used the highlighted one. When you no longer need the cache data, you can release the memory by calling unpersist. So to summarize, caching is a powerful feature in PySpark that can lead to significant performance improvements in data processing tasks. By strategically caching data that is accessed multiple times, you can enhance your application's efficiency and speed, making it especially valuable in big data scenarios. However, caching can also consume a lot of memory, so we should be very careful. Now, let's discuss about the second part of question, which is benefits of caching. So as you can see on the screen, we have total 6 benefits. The first one is improved performance. Caching allows Spark to skip expensive recomputation of RDDs or data frames when they are reused, which can significantly speed up queries and iterative algorithms. Second is reduced latency. By keeping frequently accessed data in memory, the time to access data is greatly reduced compared to reading from disk, leading to faster execution time. Third is efficiency in iterative algorithms. In machine learning and iterative computations, caching helps by keeping intermediate results in memory, avoiding repeated computations. Fourth point is resource optimization. See, caching can help balance load on the cluster by reducing disk input-output, which can be bottleneck in a data processing. Fifth point is control over storage level. With persist method, you can choose the most appropriate storage level based on your cluster's resources and workload, providing flexibility for optimization. And the last point is facilitates complex workflows. In complex data pipelines where the same data is accessed multiple times, caching simplifies the process by allowing you to reference the cached data rather than reloading it. Next question is, describe types of join in PySpark. So as you can see on the screen, we have multiple types of joins. The first one is inner join. Inner join returns only the rows with matching keys in both the data frames. Next is outer join, which returns all the rows from both the data frames with NaN in places where there is no match. Now, outer join has two parts. First is left outer join, which returns all the rows from the left data frame and matching rows from the right. Right outer join returns all rows from right data frame and matching rows from the left one. Next join is cross join, which returns the Cartesian product of both data frames. Fourth join is semi join. It returns only the rows from the left data frame that have a match in the right data frame. And the fifth join is anti join, which returns only the rows from the left data frame that do not have a match in the right data frame. See, by using DataFrame.join method, we can specify the join condition using on parameter and the join type using how parameter. As you can see on the screen, we have created a data frame called df_compylo csv.join, where we are calling join method using parameters on and how, where on specifies the column on which join will be implemented and how is for the type of join. So first line of code is for inner join and second line of code is for outer join. See, parameters called how specifies types of join, right? So here values can be inner, left, right, cross, full, outer, left outer, right outer, left anti, left semi, right? The join expressions can be appended with where and filter methods for filtering the rows. Okay, we can have multiple join too by means of chaining join method. Next question is, explain the concept of lazy evaluation in PySpark. How does it impact performance? See, lazy evaluation is a core concept in PySpark that refers to the way the framework handles transformations and actions on data. In PySpark, when you perform a transformation like map, filter, or reduce by key, the operation is not executed immediately. Instead, PySpark builds a logical plan, which is DAG, for all the transformations to be applied. Now, the key features of lazy evaluation are deferred execution, optimization opportunities, and efficient resource utilization. Let's discuss first about deferred execution. Transformations are only executed when an action like collect, count, or save as text file is called. This means that you can chain multiple transformations without triggering computation until the final action is requested. Next is optimization opportunities. Since transformations are not executed immediately, PySpark can optimize the execution plan. It can combine multiple transformations into a single stage or eliminate unnecessary computations. Next point is efficient resource utilization. By delaying execution, PySpark can better manage memory and compute resources. It reduces the overhead of multiple passes over the data, ensuring that resources are used efficiently. Now, let's discuss about the impact on performance. So first point would be reduced overhead. See, lazy evaluation minimizes the number of times the data is read from disk or shuffled across the network. which can significantly enhance performance, especially with large datasets. Next point is optimized execution plans. By analyzing the entire chains of transformations before executing them, PySpark can make decisions that lead to a more efficient execution path, often resulting in fewer operations than if transformations were executed immediately. And third point would be costly actions. Since actions trigger the execution, it is important to minimize their use within iterative process. If you can combine actions or use transformations wisely, you can improve the performance further. Let's understand it using one example. In this example, the transformations on RDD are not executed until collect method is called. So if you see, we are calling the collect method in line number 14. This allows PySpark to optimize the operations. Lazy evaluation in PySpark is a powerful feature that helps improve performance by deferring execution and optimizing execution plans. It allows the efficient resource management and minimizes unnecessary computations, making it essential for working with large datasets in a distributed environment. Next question is, what is the role of partitioning in PySpark? How can it improve performance? See, partitioning in PySpark plays a crucial role in how data is distributed across the cluster and how tasks are executed. Proper partitioning can significantly impact performance, making operations more efficient and reducing the time needed for computations. There are certain key roles of partitioning. Let's discuss them one by one. First is data distribution. Partitioning determines how data is split into small chunks, that is partitions, and distributed across the worker nodes in a Spark cluster. Each partition is processed independently, allowing parallel execution. Second role is task parallelism. By dividing data into multiple partitions, PySpark enables parallel processing. Each partition can be processed simultaneously by different executors, leading to better utilization of resources and faster execution. Third key role is reduced shuffling. When data is evenly partitioned based on the key used in operations like group by key or reduce by key, it can minimize the need of shuffling. Shuffling is an expensive operation that involves redistributing data across the cluster, and reducing it can significantly improve performance. And the last point is efficient memory use. Well-partitioned data can help avoid memory issues. If a single partition is too large, it can lead to memory overflow errors. Proper partitioning can ensure that no single partition becomes a bottleneck. Now, how partitioning improves performance? So, there are certain points as you can see on the screen. So, first point is faster computation. With data distributed across multiple partitions, Spark can utilize multiple CPU cores and nodes, leading to fast data processing times. Next point is less network traffic. When partitions are co-located or correctly aligned with the operations being performed, it reduces the amount of data that needs to be shuffled over the network. Third point is optimized resource utilization. When partitions are balanced in size, it allows Spark to evenly distribute the workload among the executors. This prevents some nodes from being overloaded while others are underutilized. And the last point is better locality. With an appropriate partitioning strategy, Spark can take advantage of data locality, processing data where it is stored, thereby minimizing data movement and latency. See, let's take an example of partitioning. You can control the number of partitions when creating an RDD or data frame. So as you can see on the first line of code, what we are doing is we are creating an RDD with a specified number of partitions. And next we are getting the number of partition using getNumPartition method. So it gives 10 partitions are available. And next what we are doing is we can also repartition an existing RDD or data frame. And for that what we are doing is we are repartitioning using repartition method. And after we repartition, when we print it, so we get the output of 5 because we wanted to repartition it to 5 partitions. And in the last section, as you can see, coalesce can also be used to reduce the number of partitions. That you can see we have used coalesce function with 2. So it is giving me the 2 partitions, right? Basically, partitioning is a fundamental aspect of PySpark that directly influences performance. By optimizing how data is partitioned, you can achieve better parallelism, reduced shuffling, enhance resource utilization, and improve overall execution speed. Understanding and managing partition effectively is key to building efficient PySpark applications. Next question is, explain the concept of broadcast variables in PySpark and provide a use case. In PySpark, broadcast variables are a mechanism to effectively share large read-only data across all the nodes in a cluster. Instead of sending copies of the data to every node for each task, a broadcast variable allows you to send the data once and have it cached on each node. This can significantly improve performance when you need to use a large dataset multiple times in distributed computations. So when we talk about the key features, broadcast variables reduce the amount of data sent over the network by broadcasting a single copy of the data to all the nodes. Also, broadcast variables are immutable. Once created, they cannot be changed. When we talk about use cases, they are ideal for situations where the same large data set is needed by multiple tasks or jobs. Okay, so let's take an example of use case, and that can be joining large data sets. Imagine you have a large data frame of user data and a smaller data frame containing user settings. If you need to join these two data sets multiple times in your computations, broadcasting the smaller setting data frame can improve efficiency. Now let's talk about the benefits. Using broadcast variables in this case minimizes the amount of data shuffled across the network, leading to improved performance during joins or repeated accesses to the smaller dataset. This is especially useful in the large-scale data processing where efficiency can be critical. So to summarize, broadcast variables are a key feature of Spark distributed computing framework. In PySpark, they are read-only shared variables that are cached and distributed to the clustered nodes to avoid shuffle operations. They can be very useful when we have a distributed machine learning application that needs to use and load a pre-trained model. We broadcast the model as a variable, and that helps us reduce data transfer overhead and it improves the performance. Next question is, describe how to implement a custom transformation in PySpark. Implementing a custom transformation in PySpark involves creating a function that can be applied to the data within a RDD, that is Resilient Distributed Dataset or Dataframe. So what can be the steps? The first would be start by creating a data frame from a data source, that is CSV file or a list or whatever it is. Next step would be use PySpark.sql.functions.udf to create a UDF, that is user defined function, that specifies the transformation, and use with column function or select function to apply the UDF to one or more columns. Let's understand it using an example. So as you can see on the screen, what we are doing is we are creating a data frame using the data mentioned at line number 9. After that, at line number 12 to 14, what we are doing is we are defining a user defined function which squares the number. And after that, we use the UDF to register the user defined function, which is line number 17. And finally, in line number 20, what we are doing is we are applying the UDF using with column to square the number available in the data. So when we talk about the output, you can see the first column shows the number and second column shows the squared values. Now let's talk about a few benefits of custom transformations. The first one is flexibility. You can define any transformations that fits your data processing needs. Reusability. Custom functions can be reused across different datasets and applications. And third is improved readability. Custom transformations can make your code clearer and more expressive. By following these steps, you can implement a variety of custom transformations in PySpark which suit your specific data processing tasks. Next question is, explain the concept of window function in PySpark and provide an example. Window functions in PySpark allow you to perform calculations across a set of rows that are related to the current row. This capability is particularly useful for operations that require context from multiple rows, such as running total, moving averages, and ranking with partition. What are the key features of window functions? The first one is window specification. Define the partitioning or grouping of the data and order of the rows within those partitions. Next is non-aggregative. Unlike traditional aggregate functions, window functions do not collapse the result set. They return the same number of rows as the input. And third is frame specification. Specify a frame of rows, that is a subset of partition, to perform calculations on, which can be dynamic. But what would be the basic structure? To use window functions in PySpark, you can typically follow these steps. Define a window specification using window function and apply a window function like row number or rank or sum, etc. on the data frame. Let's take an example. In this example, we are calculating the running total. Let's consider a simple example where we have sales data for different products over various dates, and we want to calculate the running total of sales for each product. So what we are doing here is, so we started with SparkSession and we imported window and functions. And after preparing the data in line number 7 onwards, we have created a data frame and we have used partition by function to partition the data using product. Okay. And finally, what we are doing is we are calculating the running total using sum function. So as you can see on the screen in the output, the running total is depicted. Next question is, how do you handle errors and exceptions in PySpark? Handling errors and exceptions in PySpark is crucial for building robust applications. Here are some common strategies and practices to effectively manage errors in PySpark. The first one is try except block. So as you can see on the screen, use try except block to catch exceptions in your PySpark code. It is similar to how you handle exception in standard Python. So at first what we do, we try our code and then we write the exception for it. Next is logging. So as you can see on the screen, we have imported logging library. So implement logging to capture errors and monitor your application's behavior. We can use Python's built-in logging library to log messages at various levels, and the levels could be info, warning, error, right? So here what we are doing is we have used logging.error to log our message. Next one is using DataFrame methods. Certain DataFrame methods may fail if the data does not meet expected formats or types. So we should always validate our data before applying transformations. So that's why if you see here, what we are doing is we are using a warning function from logging library. Next is handling specific exceptions. See, if you know the type of exception that can occur, like analysis exception or Py4j Java error, then catch them specifically for more granular error handling. Fifth point is validation and testing. So validate your data frame schemas and data types before performing operations. You can also write unit test to catch potential errors early in the development process. Next point is using assert statements. See, in development or debugging, use assertions to ensure that your assumptions about the data are correct. Okay, so this one can be used during the development or debugging phase. Next point is monitoring and debugging. Utilize Spark's UI to monitor jobs and identify where errors are occurring. The UI provides details about stages, tasks, and error messages. By implementing these strategies, you can effectively handle errors and exceptions in PySpark, making your data processing applications more resilient and easier to debug. Before we move to next question, let's summarize the points. So we started with try except block, then we went to logging, then we went to using data frame methods with care. Then we talked about handling specific exceptions, and after that we discussed about validation and testing. Finally, we moved to point of using assert statement during development or debugging phase, and in the last we talked about monitoring and debugging. Now let's move to the next question. Next question is, what is the purpose of checkpoints in PySpark? Checkpoints in PySpark serve several important purposes, particularly in the context of long-running streaming applications and complex data processing workflows. Here are the key purposes of checkpoints. First is fault tolerance. Checkpoints help in recovering from failures. When you set a checkpoint, PySpark saves the state of the RDD, that is resilient distributed dataset or streaming application, to a reliable storage system like HDFS or S3. If a failure occurs, Spark can restart from the last checkpoint instead of recalculating the entire lineage, which enhances fault tolerance. Next point is lineage limitation. Spark keeps track of lineage of RDD transformations, which can become very long and complex. Checkpointing allows you to truncate this lineage by saving an RDD to storage. After a checkpoint, the original RDD is no longer needed, which can help optimize memory usage and improve performance. Third point is state management in streaming. In streaming applications, checkpoints maintain the state of the streaming computation, allowing you to recover from failures without losing data. This is especially important for applications that process continuous data streams. Fourth point is data consistency. Checkpoints provide a way to ensure data consistency. By saving the state at regular intervals, you can guarantee that even in the case of unexpected interruptions, the system can recover to a consistent state without significant data loss. And finally, we have performance optimization. Although checkpointing incurs some overhead due to writing data to storage, it can lead to better performance in long-running jobs by reducing the amount of data that needs to be recomputed in case of failures. To use checkpoints in PySpark, you typically set a checkpoint directory and call the checkpoint method on the RDD or data frame. As you can see on the screen. So what we are doing here is we have set a checkpoint directory, and after that we have called checkpoint method. Overall, checkpoints are a crucial feature in PySpark that enhance fault tolerance, optimize memory usage, and ensure data consistency, particularly in streaming applications and complex workflows. Next question is, what are the differences between narrow and wide transformations in PySpark? When we talk about narrow transformation, each input partition contributes to at most one input partition. When we talk about narrow transformation, each input partition contributes to at most one output partition. In other words, there is a one-to-one mapping of partition. Whereas in wide transformation, each input partition can contribute to multiple output partitions. This means there is a one-to-many mapping of partitions. Since narrow transformations do not require shuffling data across the cluster, they are generally more efficient. Data can be processed in a straightforward manner within each partition. When it comes to wide transformations, they involve shuffling data across the partitions and nodes of the cluster. This can lead to increased latency and resource usage, as data has to be sent over the network. In case of failure, narrow transformations allow for easy recovery since only a limited number of partitions are affected. Whereas in wide transformation, recovery from failures can be more complex as a large number of partitions are affected and may need to be recomputed. Narrow transformations are less resource intensive and faster due to minimal data shuffling. Wide transformations are more resource intensive and slower due to data shuffling. A few examples of narrow transformation are map, filter, union, sample. Whereas a few examples of wide transformations are group by key, reduce by key, join. Next question is, what challenges have you faced when working with large datasets in PySpark? How did you overcome them? With this question, we can relate our own experience and tell a particular case in which we encountered challenges with PySpark and large datasets that can include some of the following points also. The first point could be memory management. Large datasets can lead to memory issues, especially when Spark tries to load too much data into memory at once. These points are just to support your experience, but you can share your own experience also in the interview. When it comes to solution, we can go for partitioning. Optimize the number of partitions using the repartition or coalesce function discussed earlier to balance data across the cluster and avoid overwhelming individual executors. Next point is tuning memory settings. We can adjust Spark configuration settings, example spark.executor.memory or spark.driver.memory based on the available resources. Next point is caching. Use the cache or persist methods strategically to store frequent access data in memory without recomputation. Alright. The next point that we can discuss is slow job execution. Generally, jobs may run slowly due to inefficient transformations or shuffling. And what could be the possible solutions that we would have used? We can discuss about use efficient transformations. We should prefer transformations like reduce by key over group by key when aggregating data, as they reduce the amount of data shuffled. Next solution could be broadcast variable. For small data sets that need to be joined with large data sets, use broadcast method to minimize data movement. Next point that we can discuss is data skewness. So uneven distribution of data can lead to some tasks taking significantly longer than others, causing bottlenecks. If you have seen such scenarios, you can obviously explain that in your interview. What could be the possible solutions? Solution could be sorting. Introduce a random key to distribute the data more evenly across partition. And next is custom partitioning. Implement custom partitions to control how data is distributed, especially when dealing with skewed keys. One more problem that we generally face is input-output performance. Reading from or writing to external data sources can be slow, particularly with large data sets. And what could be the possible solutions? The first one is optimize data formats. We can use columnar storage formats like Parquet or ORC, which are optimized for Spark and allow better compression and faster read-write operations. Next solution could be partitioning of data. When writing the data, partition it by key or date to allow the faster querying later. Another point is debugging and monitoring. See, debugging issues in distributed environments can be complex and monitoring job progress can be challenging. And what could be the possible solutions? First is Spark UI. Utilize the Spark Web UI to monitor job stages, task execution times, and resource usage, which can help identify performance bottlenecks. Another solution could be logging. Implement comprehensive logging throughout the application to track progress and catch exceptions early. One more challenge is complex data processing logic. Implementing complex data transformations can lead to hard to read and maintain code. And what could be the solution? The solution could be modular code. We can break down complex transformations into smaller reusable functions or modules. This enhances readability and maintainability. Next point is documentation. See, provide clear documentation for each step of the data processing pipeline to facilitate understanding for team members. Finally, by employing these strategies, many of the common challenges associated with large data sets in PySpark can be effectively managed, leading to improved performance and more efficient data processing. However, you can explain whatever challenges you have faced in the real-time environment. Next question is, how do you integrate PySpark with other tools and technologies in the big data ecosystem? So as you can see on the screen, we are going to talk about multiple tools and technologies. First is PySpark can read from and write to Hadoop distributed file system, which is HDFS, by using read and write methods to access data stored in HDFS. Next point is PySpark can interact with Hive for querying structured data by using SparkSQL to run SQL queries against Hive tables and ensuring Hive support is enabled when starting Spark. Next point is PySpark can consume and produce data from Kafka for real-time stream processing by using the read stream method to read from Kafka and process streams. Also, PySpark can read from and write to Apache Cassandra, which is a distributed NoSQL database, by using the Spark Cassandra connector library to integrate. Additionally, PySpark can interact with Amazon S3 for data storage and retrieval by accessing S3 buckets directly using the S3 user interface. Another point is PySpark's PySpark.ml module integrates with machine learning libraries for model training and evaluation by using MLlib for scalable machine learning algorithms such as classification, regression, and clustering. Moreover, PySpark can be run within Jupyter notebooks for interactive data analysis and visualization by installing the PySpark kernel for Jupyter and initiate a SparkSession within a notebook. And finally, PySpark can be combined with visualization libraries like Matplotlib or Seaborn for data analysis by converting Spark DataFrames to Pandas DataFrame for visualization. Next question is, what are some best practices for testing and debugging PySpark applications? Testing and debugging PySpark applications can be challenging due to the distributed nature of Spark. Here are some best practices to make the process more effective. Let's start with unit testing. So we can use frameworks like PyTest or UnitTest for writing unit tests. We can also use libraries like unittest.mock to mock Spark components, especially when testing functions that read from or write to external sources. Next is integration testing. We can create sample data frames to validate transformations and actions in our functions. We can use programs like Databricks, AWS EMR, or IntelliJ with the PySpark plugin as debugging tools. Under error handling, we can wrap our code in try except blocks to catch and log exceptions. Also, we can provide meaningful error messages to make it easier for tracing the issues. We can use configuration files or environment variables for parameters also. It allows for easier testing with different setups. Also, we can keep an eye on Spark configurations to optimize performance and resource usage. We can also use a version control system like Git to manage changes and maintain a history of our code base. Additionally, we can conduct code reviews to catch potential issues and improve the code quality. Next question is, how would you handle data security and privacy concerns in a PySpark environment? Handling data security and privacy in a PySpark environment involves a multifaceted approach. One of the best practices we can follow is to apply data encryption during processing and storage. In PySpark, we can achieve that by using AES_encrypt and AES_decrypt functions, two columns in a data frame. We can also use another library, such as the cryptography library, to achieve this goal. PySpark improves data security and privacy through encryption, access control, and integration with secure platforms. We can implement role-based access control to restrict access to sensitive data based on user roles. We can use identity and access management, that is IAM policies, for fine-grained access control to cloud resources like AWS and Azure. Under auditing and monitoring, we can implement detailed logging to track data access and transformations, making it easier to audit actions. Also, we can use monitoring tools to detect unauthorized access or unusual activity in our Spark environment. Moreover, we can classify data based on sensitivity like public, internal, confidential to enforce appropriate security measures. We can ensure compliance with relevant regulations like GDPR, implementing data protection measures, and documenting data handling processes. For secure cluster configuration, we can use firewalls, VPNs, and security groups to restrict access to Spark clusters. Under data lifecycle management, we can define and enforce policies regarding how long data is retained and when it should be deleted. We can provide training for team members on data security and privacy best practices. We can promote awareness of potential security threats and encourage a culture of data protection. We can also conduct regular assessment and audits of our Spark environment to identify and mitigate vulnerabilities. By integrating these practices into our PySpark environment, we can better safeguard data security and privacy, ensuring compliance with regulations and protecting sensitive information. Next question is, describe how to use PySpark to build and deploy a machine learning model. Although steps may vary based on the environment we are using, like cloud environments, but we can discuss on general steps. Let us consider we have an environment ready with PySpark and we start the PySpark session 2. Then as a first step, we can load the data as you can see on the first screenshot. Then we can perform necessary pre-processing such as handling missing values, feature encoding and scaling. Then we can split the data into training and testing datasets. And after that, we can select appropriate machine learning algorithm from PySpark ML Lib library. And after training, we can evaluate model's performance using test data. Once we are satisfied with our model's performance, we can save it for future use. And to use the saved models for prediction, we can load it back to our application. Next question is, describe how you would optimize a PySpark job that is running slowly. What are the key factors you would look at? Optimizing a slow running PySpark job involves several strategies and considerations. At first, let's discuss about data partitioning. We should ensure that our data is appropriately partitioned for the size of our cluster. We can use repartition or coalesce to adjust the number of partitions. We should also check for skewed partitions, where one partition has much more data than others. This can lead to slow processing. We can consider using techniques like sorting to distribute data more evenly. Now, we can use broadcast variables for large lookup tables that are needed across tasks to minimize the data shuffling. We can also use efficient data serialization formats like Parquet or ORC instead of CSV or JSON. Also, we can cache intermediate results that are reused multiple times using persist or cache methods. It avoids recomputation and speeds up the job. We can also use broadcast joins when one of the data set is small enough to fit in memory. It minimizes data shuffling. Also, we can filter data before performing joins to reduce the volume of data being joined. Also, we should minimize wide transformations like group by, join and distinct, which can lead to large shuffles. Instead, we can try to use narrow transformations wherever possible. We should also avoid using user-defined functions when built-in Spark functions can achieve the same result. UDFs can be slower because they serialize data between the JVM and Python. We should also optimize our PySpark code by minimizing the number of actions, that is count and collect, that trigger computations. Also, we should combine multiple transformations into a single action wherever possible to minimize the number of passes over the data. And finally, we should use the Spark UI to monitor our job execution. We can check stages for time taken, task distribution, and shuffle read and write sizes. We can look for stages that take the longest time and analyze the tasks within them to identify bottlenecks. Basically, optimizing a PySpark job requires a multifaceted approach, focusing on data handling, resource management, and code efficiency. By examining these key factors and using the tools provided by Spark, we can significantly improve the performance of our PySpark jobs. We should always test changes incrementally to measure their impact on performance. Next question is, how do you ensure fault tolerance in PySpark applications? Ensuring fault tolerance in PySpark applications is crucial for maintaining the reliability and robustness of data processing jobs. Spark uses immutable data structures, meaning that once a data frame or RDD is created, it cannot be changed. This helps preventing data corruption and ensures that lost partitions can be recomputed from the original data. So this is the first way of ensuring the fault tolerance. Next is Spark uses lazy evaluation, which means transformations are not executed until an action is called. This allows Spark to optimize the execution plan and recompute lost data as needed. Next point is we should use checkpointing to save intermediate results to stable storage. This is especially used for long linear chains where recomputing all transformations would be expensive. We can use DataFrame.checkpoint method for this. Another point is we should store input data in a reliable replicated storage system like HDFS or S3. It ensures that if a worker node fails, the data can be retrieved from another location. One more point is Spark automatically retries failed tasks up to the configurable number of times. The default value is 4. We can set this using spark.speculation to enable speculative execution of slow tasks, where Spark may run duplicates of slow tasks to mitigate failures. We should also implement error handling mechanism in our code, especially when dealing with external systems like databases. We should use try except blocks to gracefully handle exceptions and log errors for analysis. One more approach is using Spark's web UI to monitor job execution. We can set up monitoring tools like Apache Ambari, Grafana, or custom logging solutions to alert us to failures and performance issues in real time. We can use cluster managers like Yarn or Kubernetes that support node failures detections and resource management. This helps to recover lost executor and redistribute tasks automatically. One more point is RDDs are designed for fault tolerance. Each RDD maintains lineage information, allowing Spark to recompute lost partitions based on the transformations that created them. And finally, we can write outputs in a way that ensures consistency. Why do we use SparkConf in PySpark? SparkConf in PySpark is used to configure the Spark application and set various parameters that affect the application's execution. It allows you to customize the behavior of your Spark job by specifying settings such as resource allocation, application name, and other Spark configuration. Let's discuss some key reasons why SparkConf is important. We can set the name of our Spark application using setAppName, which helps in identifying our job in the Spark UI, which is the first key reason. Next is SparkConf allows us to specify the amount of memory and number of cores to allocate for the Spark driver and executor. For example, we can use set spark.executor.memory, 2G to allocate 2 GB of memory for each executor. Next is we can modify various Spark configurations such as shuffle behavior, the default parallelism level, and number of partitions by using the appropriate configuration keys. Next one is some features like SparkSQL support can be enabled or disabled through SparkConf. For instance, we might want to enable or disable certain optimizations or libraries. Next point is if we are running our Spark job on a cluster, we can specify the master URL like local, yarn, mesos, etc. in the SparkConf to indicate how our application should be executed. And the last point is we can also define our own custom configuration parameters that can be read later in our application. Next question is what is a DAG scheduler in PySpark? The DAG scheduler serves as the scheduling layer in Spark, managing the scheduling of tasks in a stage-oriented manner through jobs and stages. It transforms the logical execution plan, which outlines the dependency lineage of transformation or RDDs into a physical execution plan made up of stages. The DAG scheduler computes a DAG of stages required for each job, monitors which stage and RDDs are materialized, and creates an optimized schedule for executing the jobs. These stages are subsequently sent to the task scheduler for execution. The DAG scheduler performs three main functions in Spark. It computes the DAG execution for the job, it identifies the preferred location for running each task, and it handles failure caused by lost output files during shuffling. So, PySpark's DAG scheduler utilizes an event queue architecture. The DAG scheduler is an integral part of PySpark's architecture, and its presence is essential for managing the execution of distributed data processing tasks efficiently. While the underlying technologies and optimizations may evolve, the role of DAG scheduler in orchestrating execution remains critical. Next question is explain the architecture of PySpark. PySpark, like Apache Spark, operates on a master-slave architecture. In this setup, the master node is referred to as the driver, while the slave nodes are known as worker. When a Spark application is executed, the Spark driver creates a SparkContext, which serves as the entry point to the application. All operations are carried out on the worker nodes, with resource management for these operations handled by cluster managers. Let us understand better using a diagram from official documentation. So as I was discussing, we have a cluster manager and then we have the worker nodes connected with SparkContext, which is the driver program. Next question is what is the difference between RDD, Dataframe and Dataset in PySpark? So as you can see the differences on the screen. So the structure for RDD is unstructured with no schema, whereas the structure for Dataframe and Dataset is structured with schema. Type safety is not present in RDD and Dataframe but present in Dataset. API is low level for RDD but high level for Dataframe and Datasets. When it comes to performance, RDDs are generally slower but Dataframe and Datasets are faster. When it comes to use cases, we can use RDDs for complex data processing, DataFrames can be used for SQL-like operations, and Dataset can be used for type-safe operations. Next question is, what is an action in PySpark? An action is an operation in PySpark that triggers the execution of transformations that produces a result. Few common actions have been shown on the screen. The first one is collect, which returns all the elements of the data sets as an array to the driver program. It is useful for small data sets. Next one is count, which returns the number of elements in the dataset. Next action is first, which returns the first element of the dataset. Next action is take with a parameter called n, which returns the first n elements of the dataset as an array. Next action is reduce with function. It aggregates the elements of the dataset using a specified associative function, as you can see on the second screenshot of this screen. Next action is save as text file with the path. It saves the element of the dataset as a text file at the specified path. And next action is for each with function, which applies a function for each element of the dataset. See, actions in PySpark are operations that trigger the execution of transformations and return result to the driver or write data to external storage. They are essential for materializing and processing data in Spark applications, making them a critical part of the data processing workflow.